So, we continue with our discussion on nonlinear optics. Let us recall that when the electric field of the light wave becomes strong, then the polarization is no more proportional to the electric field, it has also higher order terms. So, you have something like epsilon 0 chi 2 E E plus epsilon 0 chi 3 E E E and so on. Now, this is this equation is essentially in component form an equation of this type epsilon 0 chi I j E j plus epsilon 0 chi 2 of I j k E j E k plus epsilon 0 chi 3 of I j k l E j E k E l and so on. So, please note that this E is not a dot product or a cross product, it is just E times E, and this is the short form of representing the summation over chi I j k E j E k. Ith component of polarization is proportional to the jth component of electric field through a tensor chi I j k, the linear susceptibility tensor, and these are the nonlinear susceptibility tensors. The second 2 here means it is E square term, 3 here is E cube term. So, this is responsible for second order nonlinearities, this is responsible for third order nonlinearities. Now, before we discuss the components of these tensors, we started looking at a simplified form of the polarization to understand how new frequencies can get generated. So, recall that what we had done is if I write in a scalar form, if I write the second order term, I can write this as plus epsilon 0 chi 2 E square. I just write a scalar equation representing the vector equation. We will come back and discuss in more detail how to write this equation in terms of an effective chi 2 susceptibility and so on, but right now we want to understand the fundamentals of the new frequency generation, and so we will start with some scalar equation here. And remember, as we discussed last time, if I assume an electric field of the form E 1 cos k z minus omega t, you found that if you substitute this into this equation, there is a linear component of polarization, and E square gives me a component of polarization at 2 omega frequency, and polarization is nothing but dipole moment per unit volume. So, it implies that the dipoles are also oscillating at frequency 2 omega. So, when a dipole oscillates at a frequency 2 omega, it generates electromagnetic waves at 2 omega frequency. So, that is the origin of 2 omega, but once remember, so if I take a medium, a nonlinear medium, I launch omega frequency into the medium. So, inside the medium I will generate 2 omega also. Now, this equation actually E is the total electric field. So, once 2 omega starts to get generated inside the medium, now I have electric fields at omega and 2 omega. So, if I for example write the total electric field as E 1 cos, now let me differentiate the two frequencies like this. So, I have k 1 is the propagation constant of the medium at frequency omega, plus I have an electric field now corresponding to frequency 2 omega, and k 2 is the propagation constant of the medium at frequency 2 omega. So, k 1 will be omega by c into the refractive index at frequency omega, which I call as n 1. So, omega by c into n 1. K 2 is the propagation constant of the medium at frequency 2 omega So, 2 omega by c into refractive index at 2 omega, which I call as n2. So, 2 omega by c into n2. Please note that the refractive index of the medium depends on frequency. So, electromagnetic wave at frequency omega and the electromagnetic wave at frequency 2 omega will in general not see the same refractive index. N1 is the refractive index of the medium at frequency omega, N2 is the refractive index of the medium at frequency 2 omega. So, when I launch inside the medium a frequency omega, through this E squared term I find that electric fields at 2 omega also get generated. So, the total electric field now becomes the sum of these two. So, what will happen if I substitute this into the total electric field here? So, let me look at, for example, the second term only. So, let me look at the nonlinear polarization term. So, this is epsilon 0 chi 2 into E square. So, you will have, so I substitute for E from this equation into this E square term here. So, what will I get? I will have epsilon 0 chi 2 E 1 square cos square k 1 z minus omega t plus epsilon 0 chi 2 E 2 square cos square k 2 z minus 2 omega t plus 2 epsilon 0 chi 2 E 1 E 2 cos k 1 z minus omega t into cos k 2 z minus 2 omega t a plus b whole square. So, now I write all the terms in terms of cosines. So, cos square will be in terms of cos 2 theta, and then this is cos a into cos b in terms of cos a plus b and cos a minus b. So, what will I get? I will get epsilon 0 by 2 chi 2 into E 1 square plus cos times 2 k 1 z minus omega t from the first term. Then I will get epsilon 0 by 2 chi 2, sorry, there is an E 1, yeah, E 1 square is outside, sorry, this is 1 plus E 1 square 1 plus cos twice k 2 z minus 2 omega t into E 2 square plus, so this is 2 cos a cos b. So, I can write this as epsilon 0 chi 2 E 1 E 2 into cos k 1 plus k 2 z minus 3 omega t, and then I will have one more term which is plus epsilon 0 chi 2 E 1 E 2 cos k 2 minus k 1 z minus omega t. Cos a plus b, cos a cos b is cos a plus b plus cos a minus b divided by 2. So, if you look at these terms now, this one here and this one here give you optical rectification. That means some DC polarization term. This is the frequency 2 omega, this term gives you frequency 2 omega, this term gives you frequency 4 omega, because the 2 omega frequency, once it is launched inside the medium, generated inside the medium, the nonlinearity at 2 omega frequency will now generate 4 omega frequency, the second harmonic of 2 omega. It also generates a 3 omega term and an omega term. Now, this, so the total electric field now will consist of omega, 2 omega, 3 omega, 4 omega. So, I have to substitute back into the equation and recalculate everything. Now, it so happens, as we will discuss, that to generate 2 omega from omega, I must satisfy some conditions called phase matching conditions. If I do not satisfy those conditions, the efficiency of the generation of new frequency is very, very little. I will explain this phase matching condition mathematically and physically, what is the meaning of phase matching condition, but as we will see, to generate 2 omega from omega, I need to satisfy certain phase matching conditions. Similarly, if to generate 2 omega from 2 omega a frequency 4 omega, I need to satisfy another set of phase matching conditions. Now, usually what happens, even to satisfy one phase matching condition is not easy. I have to design my polarization states, the propagation direction of the crystal, etc., to satisfy even one of the phase matching conditions. So, normally what happens is, we will be able to satisfy only one of the phase matching conditions, for example, for omega to 2 omega conversion. So, when I satisfy the condition for omega to 2 omega, I may not be simultaneously satisfying the condition for 2 omega to 4 omega term. So, this 4 omega electric field will hardly be generated. This term will not be able to generate electromagnetic wave at frequency 4 omega. This one 3 omega term also requires another phase matching condition. So, usually that is also not satisfied, but look at this term. This is a term which is generating omega. How is it generating omega? It is mixing the 2 omega and omega terms. It is the difference frequency. Omega frequency and omega frequency add to give you 2 omega frequency. 2 omega frequency and omega frequency mix to give you omega frequency, because omega plus omega is 2 omega and 2 omega minus omega is omega. So, this process, this leads to, as you can see here, a nonlinear polarization term at frequency omega. So, the same nonlinearity actually will generate from omega, it will generate 2 omega, and once 2 omega gets generated inside the medium, this 2 omega mixes with omega to generate back omega. And as I will show you, the phase matching condition for omega to 2 omega conversion is the same as the phase matching condition for 2 omega to omega conversion back. That is, omega plus omega giving you 2 omega and 2 omega minus omega giving you omega are the same phase matching conditions. So, what will happen is, if I take this medium and launch 2 omega frequency into the medium, this omega will generate 2 omega and omega mix to generate omega. So, that is a coupling. That is a coupling that is taking place between omega and 2 omega frequency. And this process, I will show you, is efficient only under certain conditions called phase matching conditions. So, although this term is generating new frequencies, it will so happen that the electric fields generated at these new frequencies will be negligible. So, usually we will neglect all the other kinds of frequencies that get generated in the process and focus on the set of frequencies for which I am satisfying the phase matching condition, and hence I will only worry about those electric fields. So, please note that when I launch an omega into a medium, I will generate nonlinear polarization at 2 omega. That nonlinear polarization at 2 omega will generate electromagnetic wave at 2 omega. The electromagnetic wave at 2 omega will mix with the electromagnetic wave at omega to generate waves at omega also. So, there is a nonlinear polarization term at 2 omega, there is a nonlinear polarization term also at omega. You cannot have a coupling in only one direction. You have omega to omega transfer, 2 omega to omega transfer is also taking place simultaneously. Okay. Now, what is the objective now? What is the objective? So, the problem is that I am given a medium in which this nonlinear susceptibility is not 0. As I mentioned to you last time, if the medium has a center of inversion symmetry, the chi 2 tensor is 0. All elements of chi I j k 2 are 0. You cannot have this process taking place in a medium which has center of inversion symmetry. So, this, let me assume this is a medium which has no center of inversion symmetry and hence can generate second order processes. So, what is my problem? My objective is I launch a frequency omega into the medium. I want to calculate how much of power am I generating at 2 omega. I launch electric field at omega inside the medium with a certain amplitude. The medium converts omega to 2 omega. So, what is the generated power at 2 omega at the output? What does it depend on? How do I maximize this efficiency of conversion? And what are the conditions under which this efficiency will be maximum, and how do I achieve those conditions in practice? So, the problem is essentially boils down to solving Maxwell's equations with the condition that the polarization now is not just the first term here, it also contains higher order terms. And right now we are looking at only this term. We will forget about all higher order terms, we will look at the contribution due to the second order nonlinearity in the Maxwell's equations. Now, to keep the mathematics simple and to understand the physics, what we will do is we will assume a scalar equation, scalar analysis in the beginning, discuss the generation efficiencies and so on, and then I will come back and look at this equation a little more carefully. Because of finally, if I give you a medium, I will tell this medium has this tensor chi I j k elements I will give you, and I will ask you what polarization of the input should I choose, what is the polarization that comes out of the medium at 2 omega frequency, what conditions should I satisfy to maximize this efficiency. So, this involves little more analysis using this tensor properties of this, but right now to understand even the basic generation of second harmonic, we will assume a scalar equation and analyze the problem. Now, before we do that, I must derive a wave equation in the presence of nonlinearity. So, let me go back and write this. So, let me write this equation. So, D is equal to, remember, epsilon 0 E plus P. This is the defining equation for the displacement vector. Now, I can write this as epsilon 0 E plus P linear plus P nonlinear. P linear is epsilon 0 chi E plus P nonlinear. This is equal to epsilon 0 into 1 plus chi E plus P nonlinear, and this is nothing but epsilon into E plus P nonlinear. Epsilon is the dielectric permittivity of the medium. So, the linear part of the polarization has been taken into account in epsilon, and this second term is the nonlinear term. So, normally D would have been equal to epsilon E. Okay, so that is the expression for D. So, let us go back and write this equation. So, we have del cross E is equal to minus del B by del T and del cross H is equal to del D by del T. Remember, no free currents, no free charges. Now, we are going to assume, as I mentioned before, B is equal to mu naught H and D is equal to epsilon E plus P nonlinear. So, let me take a curl of the first equation. So, del cross E is equal to minus mu 0. Now, I interchange the time and space derivatives. So, I get del by del T of del cross H. the first, the right hand side, the left hand side is gradient of divergence E minus del square E is equal to minus mu naught del by del T of del cross H, which is epsilon del E by del T plus del P nonlinear by del T. Now, how about divergence E? Divergence E is 0 in isotropic media. In anisotropic media, remember, D is perpendicular to k vector, E is not in general perpendicular to k vector. Divergence E is equal to 0 implies transverse condition. That means, in anisotropic media, divergence E is usually not 0. But again, to simplify the analysis here, we are going to forget about divergence E term here. But in principle, actually, divergence E is not 0 in anisotropic media. But as I left the problem to you, you can check the angle between E and D vector is not very large. Usually, it's very small. It's a couple of degrees. So I'm going to assume, as a simplification, divergence E is equal to 0, and write this as so. Let me take okay. So this is minus del square E is equal to minus mu 0 epsilon del square E by del T square minus mu 0 del square P nonlinear by del T square. So this is my wave equation, del square E minus mu 0 epsilon del square E by del T square is equal to mu 0 del square P nonlinear by del T square. Normally, when you derive the wave equation, the right hand side is 0, because normally you do not take into account any nonlinearity in the medium. So, the wave equation normally you would have obtained is del square E minus mu 0 epsilon del square E by del T square is equal to 0. The right hand side actually acts as a source for this electromagnetic field. It is an inhomogeneous equation. So, this P nonlinear is the source of the electromagnetic fields, and please note that this equation has to be satisfied for each and every frequency. So, the frequency omega will satisfy this equation for omega frequency, where epsilon will be at omega frequency, E will be at omega frequency, P nonlinear at omega frequency. For the 2 omega frequency, the electric field at 2 omega frequency, the epsilon at 2 omega frequency here, P nonlinear at 2 omega frequency. So, for example, I would have to satisfy these equations, del square E at omega minus mu 0 epsilon of omega del square E of omega by del T square is equal to mu naught del square P nonlinear at omega by del T square, and del square E of 2 omega minus mu 0 epsilon of 2 omega del square E of 2 omega by del T square is equal to mu naught del square P nonlinear at 2 omega by del T square. I showed you that there is also a nonlinear term at frequency omega because of a mixing between omega and 2 omega frequencies. There is a nonlinear polarization at 2 omega, there is a nonlinear polarization at omega, and these two equations describe the propagation of frequency omega and 2 omega through the medium, and the interaction between these two frequencies is brought about by the nonlinearity in the medium. Normally, if you have a linear medium, if you launch a frequency omega and 2 omega simultaneously, they do not interact. Omega frequency propagates independently, 2 omega frequency propagates independently. But when there is nonlinearity, the presence of nonlinearity couples these two frequencies through the nonlinear polarization term. So, in principle, if you launch only one of the waves, it can lead to the generation of the new frequency. So, now what I want to do is, so what we need to do is to generate the condition I have is I launch electromagnetic field at frequency omega. This electromagnetic field will generate P nonlinear at 2 omega. This P nonlinear at 2 omega will generate E at 2 omega. E at 2 omega and E at omega mix to generate P nonlinear at omega, which will then influence omega frequency. So, these two equations will give me a pair of coupled equations which I need to solve. I launch omega frequency, this will generate P nonlinear at 2 omega, this P nonlinear at 2 omega generates E at 2 omega, E at 2 omega and E at omega mix to generate P nonlinear at omega, which will then modify this equation. So, these two equations have to be solved simultaneously. Okay, now, I want to do a simplified analysis where I will instead of writing this vector equation, we will try to solve a scalar equation, which means we will assume that these are waves propagating in say z direction, plane waves propagating along z direction, and these are linearly polarized electromagnetic fields. So, E is along x direction, for example, is propagating along some direction z, and I will try to solve these equations in a scalar approximation, and later on I will come back and tell you this approximation, where from am I getting this approximation? If I am actually given a vector field which is different, how do I reduce the problem to this problem which I am solving now? Okay. So, remember I also mentioned that in the presence of nonlinearity, I have to use real fields always. That is why I wrote cosine there. I can actually overcome this, I can go back again to complex notation, provided the total is still real. So, the way I solved it is the following. So, for example, if I write E at omega is equal to say E1 tilde cos kz minus omega t plus phi 1. Suppose this is my electromagnetic field at frequency omega. So, I will write this as half of E1 tilde exponential I phi 1 e to the power I, let me write k1 here, k1 z minus omega t plus complex conjugate. CC stands for complex conjugate. So, I am writing this cosine as this exponential plus a complex conjugate divided by 2, and this one I write as E1 e to the power I where E1 is the complex electric field at frequency omega. It has also a phase term phi 1. Because it is of the form this plus complex conjugate divided by 2, this is always real. I am still using real notation, except that instead of writing cosine, I am writing exponential plus its complex conjugate. Yes?
Sir, E1 tilde is also a complex amplitude.
No, in the real equation, E1 tilde is real. When I write E1 tilde cos k1 z minus omega t plus phi 1, E1 tilde, everything is real. E1 tilde is real, phi is real, everything is real. But what I am doing is, I am absorbing the phase phi into the E1 tilde term and defining an E1 electric field, which is now in general complex. So, if the phase changes, E1 will change in complex magnitude, complex phase, and when you add the complex conjugate, you will get that phase inside the cosine term again. So, change of phase inside the cosine term will imply that E1 is changing with z, because phase changes with z. So, whether phase changes with z or amplitude changes with z, E1 will change with z. So, E1 is a complex electric field and the electric field at omega is written as half of E1 plus E1 exponential I k1z minus omega t plus its complex conjugate. Similarly, I will write for E2 omega half of E2 exponential I k2z minus 2 omega t plus complex conjugate, where A2 is the complex electric field at frequency 2 omega. K2 is the propagation constant of the medium at frequency 2 omega. K1 is the propagation constant of the medium at frequency omega. So, if it is an ordinary wave or extraordinary wave, K1 will have to be taken the correct value. In general, the medium is anisotropic. So, K1 and K2 are the two propagation constants of these plane waves propagating along z direction. Now, let me tell you that this z is the z direction, arbitrary some z direction. I am not, this is not the z direction of the optical of the crystal. This is an xyz coordinate system in which I am solving the problem, and this xyz need not be coincident with xyz of the principal axis system of the crystal. This is some arbitrary xyz system. Okay. So, let me write the p nonlinear term. P nonlinear is now in nonlinear optics notation, there are different kinds of notations used by different people. But what I want to do is use the following notation in which p nonlinear, remember I had written as epsilon 0 chi 2 e square. I want to write this as 2 epsilon 0 d e square, where chi 2 is represented by 2d. What will be the units of d in SI units? Look at the dimensions of p nonlinear electric field and sorry 1 by electric field, because p is has same dimensions epsilon 0 times E. So, 1 by electric field means d will be in units of meters per volt, because E has volts per meter. So, let me tell you the numbers. D is typically of the order of 10 to the minus 12 meters per volt. For media, most media, the coefficient D has this magnitude, about 10 to the minus 12, 10 times 10 to the minus 12, 3 times 10 to the minus 12, something like this. These are some numbers of media that are used in nonlinear optics. Okay, so let me substitute now this. So, what is E? E is the total electric field, which consists of E omega plus E2 omega. So, P nonlinear will be 2 epsilon 0 d. So, when I add E omega given by this equation and E2 omega given by this equation and take square. So, this factor of half will give me a 1 by 4 outside. So, I will have E1 exponential I k1z minus omega t plus complex conjugate plus E2 e to the power I k2z minus 2 omega t plus complex conjugate whole square. Okay, so, this is E square. So, from here let me pick up the nonlinear polarization terms at frequency omega and 2 omega. So, first let me pull out the term with nonlinear polarization term at frequency 2 omega, P nonlinear at 2 omega. So, can you tell me what will I get here from here? Which terms, when I take the square, I will have square of this, square of this, square of this, square of this, 2 times this into this, 2 times this into this. So, you will have a plus b plus c plus d whole square. So, can you tell me which are the terms which will have a frequency 2 omega? This square and this square. Please remember, because the total function is real, for every complex number I get, I will have a complex conjugate. So, I will have, this will be simply, so this factor of 2 and 1 by 4 gives me half. So, half, let me write inside as epsilon 0 d E 1 square e to the power 2 I k 1 z minus omega t plus complex conjugate, and there will be no other term. None of the mixing terms in this square will give me a frequency omega 2 omega. What about p nonlinear at omega? So, let me write this, let me look at this equation again. So, which product will give me omega frequency? This into the complex conjugate of the first term, because this complex conjugate has exponential plus I omega t multiplied by this will give me exponential minus I omega t. Similarly, this into its complex conjugate. So, I will have essentially half of 2 epsilon 0 d E 2 E 1 star, star represents complex conjugate, and what will be the exponential term? I will have exponential I k 2 minus k 1 z minus omega t plus complex conjugate. See, E 1 is the coefficient which multiplies e to the minus I omega t. So, E 1 square will be the coefficient multiplying exponential minus 2 I omega t. So, E 1 square is sitting here for the second harmonic polarization. E 2 is the coefficient of e to the power minus 2 I omega t. E 1 star is the coefficient of exponential plus I omega t. So, when I multiply these two terms, I will get exponential minus I omega t, which is what gives me the polarization at frequency omega. Because later on, by looking at this product, you can sort of guess the product term that will appear here and to which frequency that will correspond. For example, E 2 square would correspond to nonlinear polarization at 4 omega. E 1 E 2 will give me 3 omega. So, if you expand this, but you need to worry about the factors which are coming out in the squaring operation here. And so, this will be the nonlinear polarization at 2 omega frequency, this is a nonlinear polarization at omega frequency. So, first let me derive the equation corresponding to the frequency omega 2 omega. So, this is my equation of the electric field at 2 omega. Now, please note now that because of this generation, the amplitude, complex amplitude of the second harmonic will now be a function of z. Z is the propagation direction, because at the input to the crystal there was only frequency omega present, but as the wave propagates the 2 omega frequency gets generated. So, E 2 must have been 0 at the entrance phase of the crystal, and as the wave propagates E 2 will start to get generated, which means E 2 must be a function of z. Z is the propagation direction, and because of this nonlinearity E 2 will become a function of z. And if E 2 becomes a function of z, E 1 also has to become a function of z, because you cannot generate second harmonic unless you lose energy from the fundamental. You are only converting electromagnetic energy at frequency omega to energy at 2 omega frequency. So, if E 2 is a function of z, E 1 is also a function of z, and so in these equations I must remember E 1 and E 2 are now functions of z because of this interaction, because of this nonlinearity. So, the problem is very simple now. This is the expression for E 2 omega, E 2 is a function of z. This is the expression for P nonlinear at 2 omega, and this is the equation at 2 omega. So, if I forget about the vectors, So, I have expression for electric field, I have an expression for p nonlinear at 2 omega, I must substitute into this equation and simplify to get an equation for the development of E 2 as a function of z. I will get I'll get a differential equation for E 2 of z. So, let me do this. So, remember in this equation, wave equation, there is del square. So, this is differential del square by del x square plus del square del y square plus del square del z square. So, there is no x dependence, there is no y dependence. So, I will be only left with a z dependence. So, there will be a del z square here, there is a time derivative here, a time derivative here. So, let me now calculate what is the z differential. So, del square E 2 omega will be actually del square by del z square of E 2 omega, which is equal to del square by del z square of half. Now, let me write E 2 of z e to the power I k 2 z minus 2 omega t plus complex conjugate. Now, there is a z dependence in E 2, there is a z dependence in exponential I k to z. Okay, so, this is simple calculation. So, let me write down the final expression. I will have d square E 2 by d z square plus 2 I k 2 d E 2 by d z minus k 2 square E 2 into e to the power I k 2 z minus omega 2 omega t plus complex conjugate. It is a second differential of a product of two functions. You will have you can just differentiate that and you get these three terms here. Now, usually the rate of growth of the second harmonic with z is slow. Wavelengths are of the order of half a micron to 1 micron, but this E 2 will grow in maybe hundreds of microns slowly, it grows slowly as a function of z. So, I will neglect the second derivative of E 2 with respect to z, assuming that the growth of the second harmonic is slow, and so this is neglected. That means, in one wavelength or a few wavelengths, E 2 does not change significantly, and that is simply neglecting the second derivative. Okay. So, I substitute this del square E omega E 2 omega into this equation. I also calculate this second derivative with respect to time and on the right hand side here. Okay. So, what I need to do is the following. I substitute for this expression into this first term here. Then the time derivative is very simple because it is exponential minus 2 I omega t. So, I will get minus 4 omega square when I differentiate twice, and p nonlinear also will give me minus 4 omega square with the amplitude term sitting there. So, now let me write this equation neglecting the second derivative. So, what I will have, okay, also another thing, you have every term has exponential minus 2 I omega t and also an exponential plus 2 I omega t. If I need to satisfy this equation for all times, you can show that the coefficient of exponential minus 2 I omega t must be the same everywhere, and similarly the coefficient of exponential plus 2 I omega t will also automatically be the same on both sides. So, I just do not have to write the complex conjugate term, I only pick up the coefficient of exponential minus 2 I omega t term from each of these terms and write down the equation. So, what will I get? And remember, there is a factor of half in every term, half also I forget. So, I will get 2 I k 2 d E 2 by d z minus k 2 square E 2 into exponential I k 2 z, that is the first from the del square term. I am not writing the exponential minus 2 I omega t, because that is I am picking the coefficients of exponential minus 2 I omega t from every term and substituting. So, this minus mu naught epsilon of 2 omega into second differential with respect to time, I will get minus 4 omega square into e 2 e to the power I k 2 z del square e 2 omega by del t square gives me minus 4 omega square into this is equal to mu naught into del square del t square of this term. The factor of half is cancelled off. So, I will get, what will I get? Minus 4 omega square epsilon 0 d E 1 square e to the power 2 I k 1 z. Let me recall, I am substituting the expressions for E 2 omega and P n L 2 omega in this wave equation. In this wave equation, I am substituting E 2 omega and P n L 2 omega, and I am equating terms which are coefficients of exponential minus 2 I omega t in each of those expressions, and I will end up with this equation. Now, can you tell me what is the relationship between k 2 and epsilon of 2 omega? K 2 is the propagation constant at frequency 2 omega. So, k 2 square is equal to actually omega square 4 omega square mu 0 into epsilon at 2 omega. K is the frequency times mu naught into epsilon of the medium. This is actually if you substitute this will get 4 omega square mu 0 epsilon 0 into n 2 square. Remember, the epsilon 2 omega is epsilon 0 into square of refractive index, and what is mu 0 epsilon 0? 1 by c square. So, 4 omega square by c square n 2 square. So, this implies k 2 is equal to 2 omega by c into n 2, which is what we have assumed. So, k 2 is related to epsilon at 2 omega by frequency square 2 omega whole square, because the frequency at which the propagation constant is k 2 is 2 omega. So, 2 omega square mu naught epsilon at 2 omega. So, this term and this term cancel off. E 2 e to the power I 2 k z is common, k 2 square. So, you will have there is a minus into minus is plus. So, mu naught 4 omega square mu naught epsilon at 2 omega. So, these two terms cancel off, and this equation will get further simplified. Now, also let me take this e to the power I k 2 z on the right hand side and simplify this equation. So, what I will get is the following. So, okay, let me write it right here itself. Okay. So, I get 2 I k 2 d E 2 by d z is equal to minus 4 mu naught epsilon naught omega square d E 1 square exponential I minus I k 2 minus 2 k 1 z. Okay, minus 4 epsilon 0 mu 0 omega square d E 1 square e to the power. Okay. So, let me take this 2 I k 2 on the other side also. So, what I will get is d E 2 by d z. So, when the I goes to the right hand side, it goes to the denominator, and because of the minus sign, I take the I in the numerator with the plus sign here. So, I get I. So, now omega square epsilon 0 mu 0 is 1 by c square. So, I get 4 by 2 k 2 d E 1 square minus I, now let me call this delta k z. Now, I substitute for k 2. So, I okay, so this factor of 2 goes off. So, I omega by c into 2 by, now k 2 is 2 omega by c into n 2 d E 1 square exponential minus I delta k z. So, this is I times omega d omega square by c square, yeah, sorry. So, omega d by c n 2 E 1 square a much simplified equation starting from the equation for the second harmonic field. This tells me how the electric field of the second harmonic varies with z direction. Please notice that E 1 is also a function of z in general. So, I can't solve this equation without writing the equation for E 1, and delta k is defined as k 2 minus 2 k 1. Now, E 1 is the electric field of the incident wave at frequency omega, E 2 is the electric field of this generated second harmonic field. Now, usually what happens is in this process of second harmonic generation, the efficiencies are usually very weak, few percent, less than a percent, that is the kind of efficiency. We will calculate some numbers. So, in most situations the efficiency for second harmonic generation is not very high. What is the approximation I can make? That means E 1 is almost a constant. If there was a lot of conversion from omega to 2 omega, the energy at omega would have dropped down significantly. If that is the case, E 1 would have varied significantly, but usually the efficiencies are very low, and so as a first approximation I can assume E 1 as a constant, and then I can immediately solve this equation. So, for example, it may be possible that I take a medium, I launch 1 watt of frequency omega and I generate 10 milliwatts of frequency to omega. So, the fundamental power will go down from 1 watt to 990 milliwatts. 10 milliwatts I have generated at second harmonic, this power must have come from the omega frequency. So, the electric field of 1 watt and 990 milliwatt, which is 0.99 watts, is almost equal. So, that is the approximation which I am making here. If the efficiency becomes large, then I can't make this approximation and I need to solve this equation along with the coupled equation for E 1. Okay, so, before we solve this equation, let me look at this term here and tell you what is the meaning of this it is a nonlinear polarization term. Okay. Look at this equation. This equation tells me the nonlinear polarization is also a travelling wave. This is also a travelling wave, kz minus omega t. Now, what is the velocity of this wave? Omega by k 1, it is 2 omega by 2 k 1, which is omega by k 1, and that is the velocity of the wave at frequency omega. So, the omega frequency is propagating, it is generating nonlinear polarization which is also travelling along with it. So, omega by k 1 is the velocity of the wave at frequency of the nonlinear polarization term. So, nonlinear polarization term is propagating a velocity. So, polarization is equal to omega by k 1. What is the velocity of the electromagnetic wave? At 2 omega. Frequency divided by k 2. the velocity of the electromagnetic wave is the frequency, which is 2 omega, divided by the propagation constant at the second harmonic. Now, you see, this nonlinear polarization is the source of this electromagnetic wave, and if the source should keep on continuously feeding energy into the electromagnetic wave, these two velocities must be equal. If the source velocity and the velocity at which it is generating the wave are not at the same speed, they are not travelling together, what will happen is it will not feed continuously. The energy that is being fed into the omega frequency or 2 omega frequency will not keep on adding constructively. What is the condition it implies? 2 k1 must be equal to k2, because if these flow velocities must be equal, this implies k1 is equal to k2 by 2, which implies k2 is equal to 2 k1, which implies delta k is equal to 0. This is a very important condition called the phase matching condition. So, what I will do is we will discuss this phase matching condition in a little more detail. In the next class, we will solve this equation. We will solve this equation when delta k is not equal to 0, and I will show you that this equation tells me that for maximum conversion, for maximum efficiency, delta k must be 0. And the origin is one of the origins, physically what is happening is the source of electromagnetic field, which is the nonlinear polarization, and the electromagnetic field that it is generating must be travelling at the same speed for the energy to constructively keep on being fed from the polarization to the electromagnetic field. Okay? Okay. So, do you have any questions? Yeah.
It's not possible to use the conservation of energy with these equations, right? E1 and E2, because we ignored one term of 3 omega.
Okay. So, the question is the conservation of energy can be used? Yes, I can use the equations provided I write this equation and the corresponding E2 dE1 by dZ equation, because actually right from the beginning I am neglecting the generation of all other frequencies. So, I am consistent, I am assuming that is only frequency omega and 2 omega present, and that those two equations will satisfy the conservation of energy equation. So, whatever energy I have generated at 2 omega must have come from omega frequency. So, the sum of the energies of omega and 2 omega must remain constant as it propagates. That means I am assuming no other absorption or reflection or scattering. Okay? So, the energy conservation is still valid.